When a standard messaging app crashes, it's a minor inconvenience. Users close it, reopen it, and continue their day. But if the software controlling a commercial airliner crashes mid-flight, the outcome is immediate and fatal. If the software managing the core temperature of a nuclear power plant fails, the result is a massive, generational environmental disaster. And if a hospital's automated monitoring system calculates the wrong medication dosage, a human life is directly at risk. For these systems, engineering focuses on the identification and neutralization of catastrophic failure modes. In traditional software development, engineers usually ask one straightforward question: does the code meet the functional requirements? High-stakes engineering requires a different question: what are the potential points of failure, and how can they be mitigated? In 1986, software engineer Barry Boehm formalized a philosophy for these environments. He proposed that successful projects are the result of combining functional software with rigorous, continuous risk management. This philosophy produced the spiral model. The spiral model is a framework that organizes the development process into repeating cycles of risk detection. The traditional waterfall sequence moves strictly step by step: requirements, design, coding, then testing. But if foundational errors are discovered at the very end, it carries a severe penalty. The team must often abandon the finished code and backtrack all the way to step one. For critical systems, linear models are dangerous. They allow the most expensive risks to remain completely hidden until the budget is already spent. Rather than following a straight line, the spiral model operates as a continuous algorithmic while loop, repeating its core sequence until the software is complete. The loop begins with Phase 1, planning objectives and resources. Then Phase 2, risk analysis, isolates technological and budget threats. Next, Phase 3, development, handles coding and testing of approved features. Finally, Phase 4, evaluation, involves customer review before the loop repeats. By structuring development through these four quadrants, the methodology ensures no major coding begins without first verifying that the associated risks are mitigated. Let's trace a practical execution of this loop. Suppose the objective for the very first cycle is implementing a brand new database architecture. During risk analysis, the team identifies a significant threat. The chosen database might fail under the weight of 10 million concurrent users. Instead of building the entire application to find out, the engineers execute an isolated stress test experiment right now. If the simulation passes, the arc continues through development and evaluation, allowing the team to confidently build version 1, such as the initial login module. The loop then immediately restarts for the next feature set, like a payment module, orbiting outward into a wider cycle. With every completed rotation, the physical software grows larger, while the overarching uncertainty of the project shrinks. This early threat detection is highly effective, but it comes at a significant operational cost. Continuous risk analysis demands expensive resources. It requires hiring specialized experts, allocating extra time, and funding isolated prototype tests for every cycle. Compare a nuclear reactor's control system to a simple digital calculator application. The calculator carries almost zero physical or financial risk. This graph illustrates how development cost scales under this methodology. Even for low-complexity projects, the mandatory risk analysis forces the cost to spike exponentially, making the spiral model financially unviable for simple applications. The spiral model is strictly reserved for high-budget, massive-scale projects where failure is unacceptably costly. At a glance, the spiral model looks similar to the evolutionary model. Both rely heavily on iterating through repeated cycles and gathering continuous customer feedback. This split-screen flowchart highlights the sole critical difference. On the right, the spiral model side features a mandatory step for risk validation. It blocks progression until threats are resolved. This is the exact level of rigor demanded by defense networks, orbital mechanics, and global infrastructure. It follows the same logic used to summit Mount Everest. A climber survives by pausing at every camp to verify oxygen levels, check weather patterns, and inspect their gear. They proceed only when the immediate risks are cleared. The spiral model takes this logic of cautious, sequential exploration and applies it to the architecture of software development.